Welcome to the Explainer, everyone. I'm so thrilled you're joining us today because we're going to take a really fascinating dive into the microscopic hardware that basically makes our modern lives possible. I mean, we constantly talk about 5G, satellite communications, downloading movies in seconds, but we almost never think about the literal physical tiny hardware doing the heavy lifting, right? Today, we're looking at a record-breaking piece of tech. It's literally smaller than a fraction of a millimeter, but it holds the absolute key to our entire massive wireless future. So let's unpack the engineering brilliance behind the K-band GaN-on-SiC MMIC power amplifier.
But hey, before we can celebrate the solution, we kinda need to understand the problem. And like any good engineering story, this one has a villain. In the world of high-frequency communications, that villain is something called soft gain compression. Think of it like this. Imagine you're driving a top-of-the-line sports car, but it suddenly starts losing fuel efficiency the moment you press the gas pedal just halfway down. That's exactly what happens with traditional amplifiers. They lose critical power efficiency way before they actually reach their peak or saturated performance. It's a hugely frustrating bottleneck, and it constantly threatens the efficiency of basically all 5G networks and satellite communications worldwide.
So here's our roadmap for today. First, we'll hit the 5G bandwidth bottleneck. Second, we're decoding the alphabet soup. Third, the anatomy of the amplifier. Fourth, smashing efficiency records. And finally, why this tech actually matters. Let's get into it.
Okay, part 1, the 5G bandwidth bottleneck and the growing demand.
We're facing an absolutely unprecedented global demand for bandwidth right now. Literally everything from the commercial 5G networks down your street to complex military radar systems. They all require massive amounts of data transfer. And to handle that, we need hardware with exceptionally high power density. Now, historically, the industry has turned to gallium nitride or GaN amplifiers. And yeah, they're super powerful, but they suffer from that villain we just mentioned, soft gain compression. Basically, these traditional GaN amplifiers start compressing and losing their amplification power way too early in the process. What does that actually mean for us? It means they're just bleeding precious, expensive electrical energy long before they ever achieve their maximum saturated power. In high-demand scenarios, that wasted energy translates to excessive heat, higher costs, and really limited network capacity. Not great.
Moving right along to Section 2, decoding the alphabet soup. Let's understand these terms.
First up in our alphabet soup is the K-band. So what exactly is it? Well, the K-band is the microwave band that covers frequencies from roughly 26.5 to 30.5 gigahertz. And why does that matter to us? Because this specific, incredibly high-frequency real estate is exactly where the entire future of wireless data transfer is being built. When you hear buzzwords like 5G millimeter wave tech or next-gen point-to-point satellite communications, they are operating right here in the K-band. It is literally the ultra-fast highway of the wireless world.
Next is GaN-on-SiC, which stands for gallium nitride on silicon carbide. This is the actual physical material the chip is made of. The engineers grew a layer of gallium nitride onto a silicon carbide substrate that is shockingly thin. We're talking just 75 micrometers thick. But this specific combination of materials is absolutely crucial because it provides extreme power density and high breakdown voltages. Think of it as the perfect rock-solid foundation needed for handling intense electrical loads without physically melting down or failing.
And finally, we have MMIC. That's monolithic microwave integrated circuit. I know, it sounds super intimidating, but all it really means is that this insanely powerful amplification system isn't some huge clunky machine taking up a whole room. It is a single, fully integrated microchip. Every transistor, every capacitor, the resistors, the pathways, the whole shebang, they're all printed onto one microscopic circuit designed to operate flawlessly at those extreme microwave frequencies.
So armed with those materials, what did the engineers actually set out to do? Let's walk through their ambitious baseline targets. They wanted this chip to operate across that entire 26.5 to 30.5 gigahertz frequency range. They needed a saturated power output of more than 4 watts and a small signal gain greater than 25 decibels. But most importantly, and this is the big one for efficiency, they targeted a power added efficiency, or PAE, of greater than 30%. These were really high stakes, demanding a design that could perfectly balance raw power with extreme electrical efficiency.
All right, Section 3, anatomy of the amplifier. Let's look at the circuit design. To hit those aggressive targets, we needed an ingenious circuit design to basically act as the hero of our story and solve that early compression problem. I want you to think of this like a perfectly calculated relay race for electricity. In stage 1, a single tiny 6 by 50 micrometer device takes the incoming signal and provides the initial boost, the gain. Then, the baton is passed to stage 2, where 2 of those devices are sitting there, waiting to step up the power. Finally, the signal gets handed off to stage 3, where 4 of these devices deliver the final massive power expansion. It creates this perfect 1-to-2 drive ratio sequence, 1 device to 2 devices to 4 devices.
And this is what brilliantly illustrates the true genius of the design. How did they finally beat the villain of soft gain compression? Well, they used physics against itself. They took that first stage and biased it electrically in what's called Class A mode. Now, Class A mode is fantastic for initial gain, but it naturally causes gain compression. But then, they bias stages 2 and 3 completely differently. In Class AB mode, Class AB is highly efficient, and it naturally causes gain expansion. So by intentionally pitting the compression from the first stage against the expansion in the final stages, the two effects just perfectly cancel each other out. It's wild. They completely neutralize the soft gain compression bottleneck through pure architectural balance.
Okay, moving to Section 4, smashing efficiency records. Time to see some results.
39.8%. That is the actual power added efficiency, the PAE, that this tiny chip achieved when they tested it at 30 gigahertz. Remember their original goal from earlier? Their target was just 30%. They didn't just meet their goal, they absolutely crushed it, nearing a staggering 40% efficiency at maximum frequency. That's a real game changer.
And just to prove how flawlessly this three-stage balancing act actually worked, let's look at the numbers. For saturated power, they wanted more than 4 watts. They actually achieved 37.6 dBm, which translates to over 5.7 watts of raw power. And remember that compression gap we talked about earlier, the villain? Normally it's quite large, which means lots of wasted power. But their design brought the 1 dB compression point to within a single decibel of the saturated power. That means almost zero wasted energy before hitting peak performance. Oh, and they did all of this while maintaining an ultra-low quiescent bias of just 72 milliamps. Basically, the chip just sips power when it's sitting there waiting to be used. This dramatically outperforms previously published state-of-the-art results across the board.
Which brings us to our final section, number 5, why this tech matters and its real-world impact.
First off, this little chip is incredibly tough. Fabricated using Wolfspeed's 150 nanometer process, these devices were subjected to brutal 1,000-hour stress tests at a scorching 84 volts. The result? 0 failures. Negligible degradation. That kind of extreme physical robustness is exactly what you need to put these chips up into space for flawless point-to-point satellite communications. And down here on Earth, this high-efficiency amplification basically solves the exact hardware limitations that have been holding back the global rollout of ultra-fast 5G millimeter wave networks. Plus, for defense, it directly upgrades the efficiency, range, and thermal management of critical military radar systems. Literally, this single tiny chip makes modern, high-speed global connectivity possible. So the crucial takeaway here is captured perfectly by the author of the research paper himself, Waqas Javed. He writes, quote, "To the author's knowledge, this is the highest reported efficiency at P1 dB for a K-band 3-stage MMIC." You guys, that's not just a passing comment in a paper. That is a confident, documented claim underscoring the truly record-breaking nature of this engineering feat. They took a completely known material, they identified a persistent flaw in how we were using it, and they engineered an incredibly elegant architectural solution to achieve unprecedented efficiency.
I really want to leave you with this thought as we wrap up our explainer today. If a single 75 micrometer circuit, something literally thinner than a human hair, can completely smash global efficiency records and physically unlock the massive bandwidth potential of 5G networks, what other invisible hardware limits are out there, just waiting for a clever engineer to break them next? The physical world that dictates our digital lives is just fascinating, and it's advancing faster than ever before. Thank you so much for joining me on this deep dive into the hardware of the future. Keep questioning, keep learning, and I'll see you in the next explainer.